Hello everybody and welcome to our crash course in geometry. What we're going to do for this crash course is we're really going to kind of do it in three different components, three different parts. First thing I'm going to do is go through some of the basic underlying components of geometry that you really need to know in order to compete in the course. And then we're going to go through various aspects of the various chapters in the book. Then at the very end, we're going to go over the homework. That's really going to be a totally separate section of this crash course. And let us go through. Let's start with this is the study guide, the sessions that you have access to. Hopefully, you have access to them. If you don't, you should get access to them because they're important and they could be really good. And we're really just going to cover some basic ideas of geometry that are very important. The basic fundamental building blocks of geometry include angles. An angle is where any two lines or line segments meet. A line, incidentally, is a line is something that goes goes infinitely in each direction. A ray has one endpoint and goes infinitely in the other direction, and a line segment has two endpoints. If you see, for example, AB, and that has to be a line segment. So, I mean, if it ends at A and ends at B. If you have a line over here and you have A on one side and you have B on the other, you have an A here and a B here, this has to be a line segment. Angles are measured using degrees. Now, a full circle, in other words, all the way around, is 360 degrees. You're going to see that over and over and over again. For a full circle is 360 degrees. So an angle is really measured as a percentage of the circle. An angle could be a relatively small angle like this, or it could be an enormous angle like the other way around. Now, for example, over here you could have a small angle, which is the one that's already marked. Or you can look at these two lines as being a really big angle. This angle, the small one, is probably going to be about 30 or 40 degrees, whereas the bigger one is going to be almost 360. It's going to be more like 330 degrees. The point is, the maximum an angle could be is 359 degrees. No such thing as a 360 degree angle, because that's the same thing as a 0 degree angle, because then you've literally come full circle. An example given over here is when you're talking about like a pizza pie. Well, if a pizza pie is, some pies are made with 6 slices, so then one slice is 1/6 of the pie. If you wanted to measure how many degrees that is, that would be 1/6 of 360, or 60 degrees. If it's 1/9, of course, it would be 40 degrees. If it's 1/8, it would be 360 divided by 8, which is 45 degrees. So it's really, every angle is really just a percentage of the full 360 degree circle. There are also some types of special angles. There is a right angle. A right angle is a 90 degree angle. It's called a right because it makes a right turn. You go down, you go up here, and then bang, you make a right turn and go over here. Could be a left turn also. It depends on you're coming from the other direction, but nevertheless, it's called a right angle. A right angle is 1/4 of the circle. And it's very important because it's, first of all, it's nice and neat and elegant, but there are also many mathematical properties that only occur when you're talking about right angles. Then you have a straight angle. You could call this a straight angle, or you could call this a straight line, 180 degrees, straight down the middle. That should be fairly obvious. There are also different types of angles based on their numbers. An acute angle is something less than 90 degrees. An obtuse angle is between 90 and 180. More than 90 degree angle, like this sort of thing, and like this, the big black line that we saw before, that would be what's called like a reflex angle, because you're reaching all the way back. You're reflexing. A couple of very important points when it comes to angles, and that is angles that are next to each other have particular properties. Angles that are opposite each other are equal, and angles that are next to each other on a straight line, when you have two straight lines crossing, opposite angles are equal to each other, and adjacent angles that are next to each other on a straight line that comprise an entire straight line, have to equal 180 degrees. And the reason for that, of course, is because a straight is 180. A straight is a full straight line, and So let me just make this a little bigger to illustrate what I'm talking about. Okay, let's say we have this. This line, these are all Greek letters, alpha, beta, and two other letters which I don't recognize, but that doesn't matter. The point is this angle is equal to that angle. They are what are called vertical angles. They're opposite angles on the same side. Angles that are next to each other, for example, alpha and beta, these two, have to equal to 180 altogether. The reason why they have to equal to 180 altogether is because altogether they make a straight line. And those are what are called supplementary angles. Supplementary angles must equal 180. You could have two supplementary angles, or you could have three or more supplementary angles. If I make a line, let me make a line, and then I've got a whole bunch of crisscrossing lines. I got a line over here, and I've got a line over here, and they crisscross at the same point. If I'm talking about three angles, let's say I'm talking about this angle, and that angle. These angles combined are supplementary. If you add it up, angle A, angle B, and angle C, they have to equal 180 altogether. There's also something called complementary angles that equal up to 90 degrees, and we could discuss that later, but now that we're on the topic, might as well discuss it now. Let's say you've got two lines that form in a right angle. These lines are also called perpendicular to each other. They form in a right angle, which means that the symbol for that is this, which means that they're at a right angle, which means together they're 90. This angle is a 90-degree angle, but imagine we've got a line that goes like this. So you've got two angles here. You've got angle 1 and angle 2. Well, since this whole angle has to equal 90, it's also true to say that angle 1, this is the symbol for angle, plus angle 2 has to equal 90 degrees. These are also what are known as complementary angles. Okay. Okay, then we've got some rules regarding parallel lines. These are some very interesting rules. The rules regarding parallel lines means two lines that will never meet each other. They go side by side. If you look at line 1 and line 2 in this kind of diagram, they are never going to meet. If there is a line that cuts through both of them, that line is now called a transversal, and a transversal has certain unique properties to it. Let me get this onto the board where I can draw on it. So here we go. Let's make this a little bit bigger. Okay, a couple of unique properties. First of all, as we already discussed before, nothing to do with parallel lines. 1 and 4 have to be equal to each other because they're vertical angles. 2 and 3 have to be equal because they're vertical angles. 3 and 4 have to be supplementary because they're on the same line. 1 and 3 have to be supplementary because they're on the same line. But when you have two angles, it's also a fact that 4 has to be equal to 5. And the reason why is because these are called alternate interior angles. And when two parallel lines are cut by a transversal, in this case little l is a transversal, alternate interior angles are equal to each other. So 4 and 3 are equal to each other. So interestingly enough, if I know what one of them is, I'll know what all 8 of them are very easily. For example, if you tell me that angle 1 is 50 degrees, well then angle 4 also has to be 50 degrees. Angle 3 is supplementary with angle 1 or angle 4, so it has to equal 180 altogether, which means there has to be 130. This also has to be 130. Now, because 5 and 4 are alternate interiors, 5 has to be 50. 6 and 3 are alternate interiors, so 6 has to be 130. You also knew that 6 had to be 130 because it's supplementary with 5. And then 7 has to be 130, and 8 has to be 50 degrees. So you can see how once you get one of them in these kinds of situations, getting the rest is actually very, very easy. Okay, so those are some of the rules regarding parallel lines. Okay. Next, let us take a look at polygons. Polygon is a shape that has 3 or more sides. Now, a shape has to have more than 3 or more sides in order to be completely closed in. But the most basic type of shape is a triangle. Triangle's got 3 angles. That's why it's called a triangle. A, alpha, beta, and I guess gamma over there. And the alpha, beta, and gamma together have to equal 180 degrees. That's always the rule. In fact, the rule regarding any polygon is that the number of degrees all of its angles have to equal up to is the number of sides minus 2 times 180. Basically, 180 for 3 sides, and then another 180 for 4 sides. So a quadrilateral, a 4-sided figure, has to have 360 degrees. A pentagon, which is a 5-sided figure, would have to have 540 degrees. For every additional side you add, you just got to pop on another 180 degrees. So, for example, a 10-sided figure, well, let's say a 12-sided figure. A 12-sided figure, you take this number of sides minus 2, which is 10, multiplied by 180. Altogether, if you add up all the degrees in a 12-sided figure, all the angles in a 12-sided figure, you'd have altogether 1,800 degrees. And that is true in general for triangles, of course, as well. Triangle, of course, has to have 180 degrees. It's also true, of course, in this diagram that alpha, beta, and gamma have to equal up to 180 because they're in the triangle, and also alpha, beta, and gamma over here have to equal 180 because they're all in the same straight line. Okay, now let us move to the issue. Well, let's move to there in the next clip. The next subject is the subject of area. Now, area means it's a 2-dimensional phenomenon rather than 1-dimensional. When you're talking about lines, well, a line is, let's say, 10 feet. On the other hand, when you're talking about the area that you have in a backyard, the area that you have on a table, whatever it is, it's 2 dimensions, length and the width. It's like for you, if you have a 10-foot by 10-foot table, well, then the total number of square feet, the total amount of area on the table would actually be 100 square feet. And that's because squares have a certain way of measuring area, but all different polygons have various different methods of measuring area. You can see over here, obviously the introduction is that the triangle on the right is larger, has a larger area than the triangle on the left, but we have to figure out a way to quantify that. This is a basic idea of what area is. For example, if you have a rectangle that is 1, 2, 3, 4, 5, 6, 7, 8 by 4. Well, if it's 8 by 4, even though if it would actually be there are 8 boxes going this way and 4 boxes going that way. If you count them up, there are actually 32 boxes. So the length may be 8, the width may be 4, but the area is actually 32 boxes, 32 square units. If it was just 1 by 1, if one little box, one high and one wide and one tall, then the area would only be 1 unit. But the more you get in terms of area, the higher the more you get in terms of length and width, the higher the area goes. So this would actually be 32 square units over here. So, and the same thing is true, of course, if you have a half a unit. If you have, for example, a 2.5 unit, then you just do 2.5 times 4. It's 4 wide, 2.5, or 4 is the length, 2.5 is the height, so you can have a half a unit. So 4 times 2.5, which is 10 square units altogether. Now, to figure out the area, there are various formulas based on the shapes. First thing I want to discuss is triangles and something called a parallelogram. Now, a parallelogram is really just a type of quadrilateral. Even before we get to 4-sided figures, which parallelograms are, let's do the triangle first. The triangle, the way to figure out the triangle, the way to figure out the area of a triangle, is the base times the height divided by 2. For example, if you have a right triangle, which would be this, for example, Sorry, I'm not. Okay, finally managed to draw a triangle that are fairly straight. Well, the base times the height, or the length times the width. Base times height and length times width essentially mean the same thing. This would be the height, this would be the base, or you can call this the length and that the width, makes no difference. So if this were a four-sided figure, I mean, if you can visualize it, if this were a four-sided figure, just like the one we saw before, then it would look something like this. And whatever. Okay, not perfect drawing. But then the area of the entire thing, including the green area, would be the base times the height, or the length times the width. Now, a triangle, as you can see, is kind of cut in half, and therefore the formula for area of a triangle is 1/2 times the base times times the base times the height, or base times the height divided by 2. You can also write it 1/2 of the base times the height. And if you look at it something like this, I think it's fairly self-explanatory as to why that is. Now, sometimes you might not have the height right away. For example, if you have, what we would consider a normal-looking triangle, something like this, you might not know exactly what the height is. It might be easy to figure out what the base is, but the height, you'd have to figure out what the length is from the top to the bottom. The height doesn't mean any of the diagonal sides. The height means how long it is from the apex to the bottom of it. So really, if you wanted to figure out the area of the triangle, first you'd have to figure out how far it is across, then you'd have to figure out what the height is, and then you would be able to figure out the area of a triangle. Now we're going to move to quadrilaterals. I want to teach you a little bit about what the various types of quadrilaterals are. And there are some types of quadrilaterals that are, just simply random quadrilaterals that have no particular rhyme or reason. I could make a four-sided figure that just looks like this. This, and this. I mean, this is a quadrilateral. There may not be any particular method to it. It just could be just a random quadrilateral. We're not going to deal with those for the most part. We're going to deal with specific types of quadrilaterals. And the first overall type of the quadrilateral is something called a parallelogram. Parallelogram is a parallelogram is any four-sided figure where the opposite sides from each other are both parallel. So for example, here, it might look something like this. Anyway, so the point is that assuming this is a parallelogram, there are certain rules that it follows. First of all, opposite sides have to be parallel. That's the symbol for parallel. This side is parallel to that side. It also means this side is parallel to that side. Opposite sides are parallel. There are also some other rules that are important to know regarding parallelograms. Number one, opposite angles are equal. This is equal to this, the ones in the corner. And this, I'll use 2 because we're doing a different one, is equal to this. Opposite angles are equal. Opposite sides are also equal. This is equal to this, and this is equal to this. And finally, the last rule regarding the parallelogram that is important to know is that if you draw diagonals across the parallelogram, they bisect each other. Diagonals bisect each other, which essentially means that this part of this line will be equal to that part, in other words, on either side of the place that they crisscross, and this part will equal this part. Diagonals bisect each other. Those are the rules that apply to all parallelograms. Opposite sides are parallel, opposite angles are equal, opposite sides are equal, diagonals bisect each other. That's true for all parallelograms. Now, there are also a bunch of subtypes of parallelograms that you're probably more familiar with, and I'm going to go through the rules of each one of them now. Let's take first at the rectangle. Now, a rectangle looks something like this. Okay. I mean, presumably you've all seen, or you all basically know what rectangles are. But still, let's draw one. Okay. All right, so there we go. That is a rectangle. Now, all a rectangle is a parallelogram that has at least one right angle. Because if it has one right angle, by definition, it has to have four right angles. And the reason for that is, oh, by the way, one more thing. Consecutive angles in a parallelogram have to equal 180. This plus this has to equal 180, which is common sense because it's a quadrilateral, so all the angles together have to equal 360. And if all the angles together have to equal 360 and the opposites are equal to each other, then each side has to equal a total of 180. Now, if you know that this is a parallelogram, if I call this A, B, C, D, and I tell you that A, B, C, D is a parallelogram, and this is the symbol for parallelogram, just like a box, and I tell you that B is a right angle, well, then they all have to be right angles, because if B is a right angle, well, then C is across from it, so it also has to be a right angle, and C and D have to equal up to 180, and if C is 90, so D also has to be 90, which means A also has to be 90. So a rectangle is a parallelogram. Of course, opposite sides are equal, but that's true in any parallelogram. Opposite sides are equal. And all the same rules apply as in a parallelogram. So let's mark this as a rectangle. Okay. The third type of parallelogram is none other than the rhombus. A rhombus is a parallelogram where all four sides are equal to each other. It has to be a parallelogram. Actually, the truth is, a rhombus is inherently a parallelogram. The thing that decides a rhombus, or that defines a rhombus, is if all four sides are equal to each other. If all four sides are equal to each other, you know right away that it has to be a rhombus. Now, there are a couple of things about a rhombus. First of all, of course, it has all the same rules as a parallelogram does. The additional thing that a rhombus has, the opposite angles are equal to each other, of course. This angle is equal to this angle, this angle is equal to that angle, is that when you have a diagonals in a rhombus, they are perpendicular to each other, which means that this angle over here makes a 90-degree angle. That's just one of the, looks like kind of like a kite when you do that. Anyway, so a rhombus, by definition, their diagonals cut each other at a 90-degree angle. Then there's even a subtype of rhombus that I'm sure you're all familiar with. There is a type of rhombus that looks something like this. And this you all know as a square. In fact, let me write that down for both over here. This is a rhombus. And this is a square. The relationship between the parallelogram and the rectangle is kind of the same as between the rhombus and the square. Let me get rid of that tail over there. But all right, I just made a bigger one. Anyway, a rhombus is a square is a rhombus that has a right angle. Because if a square has one right angle, then of course it's a parallelogram, so it has to have all right angles. And so if you have right angles plus all sides are equal to each other, then you've got a square. And a square, I mean, everything is equal. The diagonals are equal to each other. If there are diagonals, the opposite sides are equal. All the angles are equal. The diagonals not only are equal, but of course they also form right angles. Pretty much everything is equal in a square. A square is as elegant a figure as you're going to get. Here's one basic rule for all of them in terms of the area. Figuring out the area of a parallelogram is very easy. Figuring out the area of a parallelogram is the base times the height. Now in a square or a rhombus, that's really simple. Base times the height, their base and the height are the same. So you just do any side to the second power. In a rhombus or a square, the area is any side squared, because base and the height are the same thing. So to the second power. A rectangle is base times the height. Just take the base, multiply by the height, and away you go. For the parallelogram, it might be a little more complex, because the base might be easy to figure out. The height might be a little less easy to figure out, because, this is not necessarily the height. On the angle, you'd have to draw, a straight line going down to the corner over there and figure out a way to get this in order to figure out what the height is. But if you do know what the height is, so it's the area of a square, the area of any parallelogram is the base times the height. And finally, I've got one more type of one more type of quadrilateral, four-sided figure, that I would like to introduce to you, and that is the trapezoid, which I'm going to bring to you as soon as I can draw a straight line. All right, close enough. Anyway, a trapezoid is a quadrilateral that has only one pair of parallel sides. This is parallel to that. Nothing else is the same. This side is not necessarily equal to that side. This angle is not necessarily equal to that angle. None of the parallelogram rules apply because only one side is equal to each other. Now, the area of a trapezoid. Now, there's such a thing, of course, as an isosceles trapezoid, where the two sides are equal, just like an isosceles triangle. I'll get to that in a minute. But the way to figure out the area of a trapezoid is also the base times the height, but the problem is there are two different bases. The height is the same, of course, for the whole thing, but there are two different bases. There's a bottom base and a top base. So the average base, it's the average base times the height. Or, if you want to look at it from a mathematical perspective, base 1 plus base 2 divided by 2 times the height. Base 1 plus base 2 divided by 2 is obviously the average base. If this is 10 and this is 8, and the height we'll call 4, we have to figure out the height. It's not necessarily the length of these sides over here. These are curved. But if you figure out that it's 4, well then the average base is 9, because 10 plus 8 is 18. And so the average base is 9. 9 times 4 is 36. So this would be this example would be 36. While I was on the subject of triangles, I mentioned already how to figure out the angles of the angle of a triangle. The area of a triangle, excuse me. There are three basic types of triangles that are important to know in terms of the relationship between the sides. Some triangles have two sides that are equal to each other. This is what is called an isosceles triangle. Again, an isosceles triangle, this is equal to this, but the third one is not equal to each other. That's called isosceles. Going to be very, very important as we move along. Isosceles triangles have also one important feature, and that is that the angles that are at the bases are also equal to each other. So in an isosceles triangle, this angle is equal to that angle. Then you have an equilateral triangle. Equilateral triangle is a triangle where all three sides are equal to each other. Okay, again, this, I don't know if this, yeah, this doesn't really look like an I don't know. Well, anyway, just pretend, just pretend that all these sides are equal to each other. That's an equilateral triangle. That's outside the triangle, so we don't need to worry about it. So if all these sides are equal to each other, that is an equilateral triangle. Then you have triangles, something called a scalene triangle, which none of the sides are equal to each other. You can also have something called a right triangle. A right triangle is a triangle with a right angle in it, which has all sorts of interesting properties terms of trigonometry, in terms of geometry. There, and this is what a right triangle looks like. It has a right angle in it, and this, of course, right angle is 90 degrees, which also, of course, means that these two also have to add up to 90, because it has to be 180 altogether. This side over here is what is known as the hypotenuse. The other sides are called legs. Well, each one is a leg. The hypotenuse has to be the longest side because it is opposite the largest angle. So this is the hypotenuse, these are the legs. Very important type of triangle. You can also have an isosceles right triangle. It could be both. If the two legs are equal to each other, if this happens to be equal to this, then it's a right triangle, and it's also an isosceles triangle. Okay, so those are the introduction to the triangles, and this we already did. Trapezoids, and we figured that out, of course, using figuring out the height and taking the average of the bases. Okay, and finally, well, not finally, but the next issue regarding a right triangle is that in a right triangle, and let me get rid of the other triangles because now we're talking about right triangles, you've got, let's draw a new right triangle. Okay, here's a nice, fresh right triangle, and we define it as a right triangle by putting a right angle over here. That's the symbol for a right angle. Okay, so now, the famous Pythagorean theorem, which you're going to use probably more than any formula in this course, says that the square of the legs added together equals the square of the hypotenuse. So if we call this side A, and this side B, and this side C, with side C always being the hypotenuse, A squared plus B squared equals C squared. So for example, let's say for argument's sake A is 3 and B is 4, and we don't know what C is. Well, we could simply say 3 squared plus 4 squared equals C squared. And then we would solve this like any other equation. 3 squared is 9 plus 4 squared is 16 equals C squared. And to get C, you would take the square root of each side to isolate C. 9 plus 16 is 25. So that would be, you would take the square root of each side, and your answer would be 5. So C would be 5. You can always figure out, sometimes it's going to be an irrational number, it's just going to be a square root, but you can always figure out, as long as you have two sides of a right triangle, you can always figure it out. What if, for example, you have the hypotenuse, but you don't have one of the legs? Let's say you have, all right, let's get rid of this over here. So let's say you have, this side is 8 and this side is 17. And you want to know what this side is. Again, A squared plus B squared equals C squared, where C is the hypotenuse. So 8 squared plus X squared equals 17 squared. 8 squared is 64 plus X equals 17 squared, which is 289. Subtract 64 from each side to isolate the x, basic algebra. X squared equals 225, and you take the square root of each one, and x equals 15. Again, it's not always going to come out to a perfect square. I can tell you a little tip, a little trick. There are only three types of right triangles that are going to come out to nice, whole, even numbers like this. And that is the 3, 4, 5 triangle, the 5, 12, 13, and the 8, 15, 17. This means that if the hypotenuse is 5, The legs it can be 3 and 4. If the hypotenuse is 13, the legs can be 5 and 12. If the hypotenuse is 17, the reason is because the squares add up to each other. 3 squared is 9 plus 4 squared is 16 equals 25. 5 squared is 25 plus 12 squared is 144 equals 169, which is 13 squared. And as we just saw, 8 squared is 64, 15 squared is 225, and then they add it up to 289, which is 17 squared. And it can also be multiples of this. For example, it could also be 6, 8, and 10, because that's really a 3, 4, 5 triangle that's just doubled. It could be 15, 24, and 15, 36, and 39, because that's simply a 5, 12, 13 that is tripled. In other words, any multiple of these sides to a square. If you don't have to remember these, you can apply the Pythagorean theorem every time, but you will eventually remember them once you do enough Pythagorean theorems and you realize that these work. It hopefully will become second nature to you. Okay, and finally, I want to discuss a little bit about circles. Now, here we've got a circle. Maybe not an exact circle, but it's close enough. So we're going to use it. Now, a circle, of course, has 360 degrees altogether. A circle has two things that you need in terms of formulas. One is the circumference. Circumference means how long is this outer end? If I were to start over here and take a walk all the way around the outer edge of the circle, kind of like the perimeter that you would have when you're talking about a shape, but a circle has a circumference, and a circumference is pi times 2 times the radius, which is the same thing as pi times the diameter. The radius of a circle means the length from the middle to any of the edges. Every radius in this circle is the same. If, for example, you draw a line from here to here, or a line from here to here, or a line from, if this is the center of the circle, obviously that's a big if. In my example, it probably is not a great line, but again, from here to here, from here to here, these are all radii. They all have to be the same. They're all exactly half the distance as if you would go all the way across. If you do have a line that goes all the way across from one end to another, that goes through the middle, this is what is called a diameter. And it's the same thing, of course, as 2 times the radius. So the circumference of a circle is the diameter, whatever the diameter is, times this number called pi. Pi is a constant number. It's always the same. And it's an irrational number. It goes on forever. It's approximately 3.14. It's even closer to a fraction of 22/7. But if it's 3.14159, and then a whole bunch of places after that is the exact number. It goes on forever. But for our purposes, when we're dealing with these numbers, we're just going to round it off to 3.14. It's close enough to get you pretty close to what the actual correct answer is. So anyway, that's the area of a circle. Pi times the diameter, or 2 times pi times the radius. Same thing. The area of a circle, on the other hand, is pi, again, times the radius squared, times the radius to the second power. So let's say, for example, the diameter is 10. Now, and I ask you to give me both the circumference and the diameter. Well, the circumference is easy. 10 times pi, 10 times 3.14, about 31.4. The radius, the area is pi r squared. What's the radius? Well, not 10. 10 is the diameter. The radius is only half that. So that's 5. 5 squared is 25, so the answer is 25 times pi. Usually you can just leave your answer in terms of pi. You can just say 25 pi. If they ask you to the nearest hundredth or whatever it is, then do 3.14 times 25, and you'll get the answer that way. I'm not going to spend a lot of time on the volume chapter. Volume is essentially the third dimension. when you're measuring the third dimension. Remember, the first dimension is just length. It's 10 inches long. It's 100 miles long, whatever. Then you have the second dimension, which is area, 100 square feet, 10 by 10. We've discussed that. Volume is when you have the third dimension. Now, if you have a cube, which is a three-dimensional square, a box, essentially, well, then it's really simple. Just take the dimensions are all the same. In a cube, the dimensions are all the same. Let me get you a new cube. Looks something like this. A cube looks something like this. It's a box. Now, in order for it to be a cube, all the dimensions have to be the same. It's kind of like a square, but in 3 dimensions. This has to be the same as this, which has to be the same as this. Now, for that, you just use any edge to the third power. So, for example, if this is 10 tall, so the volume of this cube is 10 times 10 times 10. 10 height, 10 width, 10 depth. And 10 to the third power is 1,000. If this is not equal, if this is not a cube, in other words, let's say, for example, this is 10, but the length is 12. The height is 10, the length is 12, and the width is 8. Well, then again, just simply multiply them all by each other. In this case, you have 8 times 12 times 10. 8 times 12 is 96, times 10 is 960. That would be the volume, like in cubic feet or cubic inches. That would be the volume of a of a rectangular solid like this sort of rectangular box. Okay, then you have kind of like the parallelepiped, which I guess is kind of like a parallelogram, except with 3 dimensions. And there you use essentially the same base times height times width to figure it out. A cylinder, which is kind of like a can, is something that has a circle, but it also has a height, like a can. I mean, I can't really describe it any better than a can. The way to figure out the area of that, just like with a cube or a rectangular solid, you were doing the base times the height times the width, or the base times the height times the depth. The same thing is true with a can. With a can, you need the bottom, the area of the bottom, essentially. Let me show you what I mean here. First of all, let me copy and paste this into my paint so that I can draw on it. All right, where is it? Oops. All right, this is a can. So in order to figure out the area, or excuse me, the volume of a can, I would need to do the area of the circle, in other words, the area of this whole thing down here, the area of the whole B, where I'm drawing here, multiplied by whatever the height is. How do you figure out the area of a circle? The answer, of course, is pi r squared. So the volume of the can is pi r squared times the height. Just the bottom times whatever the height is. Simple enough. Okay, just a cone I wouldn't worry about all these different types of cones. A cone is kind of like a can, except it's only 1/3 the volume. If you take this can and you kind of slice a cone out of it, and it looks like this, it's 1/3 times the base times pi r squared h in this sort of a scenario. You have to figure out pi r third times h, pi r to the third power, pi r squared h. You have to figure out pi r squared h and then divide it by 3 in order to get a cone, because the fact that it comes up and narrows as it goes up takes 2/3 out of it. These are different types of cones. And then you have a ball, a sphere. A sphere just happens to be 4/3 pi r cubed. Because the whole thing is a ball. There's no height. So you just take the radius, cube it, multiply it by 4/3, and multiply it by pi. Again, I don't really know anything that you can do to know it other than just to really remember it. The next lesson is about proportions. Now, proportions are important for the concept of similar triangles, which we'll discuss a little bit later on, and it is also important for some of the theorems with regard to circles, with regard to the lengths of circles, secants, tangents, and all the stuff that we will consider later on. The idea of proportional is that things are based on the same ratio. For example, if one side of a triangle is 2 and another is 4, well, you might have a different triangle where the sides are 4 and 8. Or two of the sides are 4 and 8. Now, those two pairs of numbers, the 2 and the 4 and 4 and the 8, are proportional to each other. In other words, as one doubles, the other doubles also. Here are some examples of fractions that are proportional. For example, 2/6 is the same as 4 over 12, which is the same as 9 over 27. If you notice, each of these examples reduce to 1 over 3. So, of course, the fractions are the same. And if you had two measurements, one was 2 and you had 3 sets of 2 measurements each, a 2 and a 6, a 4 and a 12, and a 9 and a 27. Obviously, they're very different sizes from each other, but they are proportional to each other. The shapes, or whatever they make up, their lengths, are proportional to each other. But of course, the bigger numbers have to be in the same side of the fraction. This also works. 6 over 2 is to 12 over 4 is to 27 over 9 because they all reduce to 3. 6 divided by 2 is 3, 12 divided by 4 is 3, and 27 divided by 9 is 3. This, on the other hand, of course, does not work. You have a 2 over 6, and you have the same numbers. You got a 27 here and you've got a 9, but you don't have them in the correct order. They don't all reduce to the same fraction. 2 over 6 is 1/3, 4 over 27 is a little less than 1/6, and 12 over 9 is about 1 1/3. You had the same numbers, but the order is very important. That's going to be very important when it comes to similar triangles, because similar triangles only work, the proportions only work. You can only glean things from the proportions if they are in the same order. This becomes relevant to similar triangles. Now, if you look at similar triangles, sometimes you refer to the original one as ABC, and then you refer to the new one, the second one, as A prime, B prime, C prime, prime being that little squiggly thing up here. So these two triangles are proportional if the angles are the same as each other. A has to be the same as A, B has to be the same as B prime, or C has to be the same as B prime. If they have all the same angles, now obviously these two triangles are not the same size. They're very, very different sizes, but they are proportional to each other if the corresponding angles are the same. Now, the way you prove congruence, and that's something we cover in a different section, of course. The way you prove that two triangles are exactly the same, they can literally fit on top of each other, is if the sides are all equal to each other and the all angles are equal to each other. Now, as we'll see, there's other ways you can prove it. You don't literally need to prove every side and every angle. Certain combinations of those sides and angles also prove congruence. But similarity, which is different than congruence, congruence is complete equality, whereas similarity only means equality of the angles. That can be proven simply by establishing that 2 out of the 3 angles are equal. For example, if I say that angle A is equal to angle A prime and angle B is equal to angle B prime, well, the triangles have to be similar to each other, because C has to be equal to C prime. If A is equal to A prime and B is equal to B prime, well, every triangle's got to equal up to 180 altogether. So if A and B are equal to each other, the same number of degrees is going to be left over for C. So to establish a similar triangle, you only have to establish that 2 of the angles are equal to each other. You only have to prove that. Once you have established that they're similar triangles, well, then the side lengths are in proportion. So, for example, in this sort of set of similar triangles, if I, for example, tell you that angle A is equal to angle A prime and angle B is equal to angle B prime, I'll use one angle sign to denote equality of this angle, and 2 to denote equality of that angle. That means that these are similar triangles. It also means that C is equal to C prime, but it also means that the ratio of the sides are in proportion. So, for example, if I say that this is 4, and that's 5, and that's 2, let's say, Now, so if I tell you that this is 12, well, then I can figure out these other two sides also, because they're all in proportion. This is 3 times the size of that, so this side also has to be 3 times the size of the corresponding side, which is 15, and this has to be 3 times the size of this, which of course is 6. It's also true, of course, that when dealing with similar triangles, you do have to make sure that the correct angles correspond to each other. In this example over here, you have two similar triangles. Certainly they are similar. You see the angles are all equal. This is 100, that's 100. That's 30, that's 30. That's 50, that's 50. So the two triangles are similar, but you have to understand that the proportionality, and the sides are in proportion, are relative to where the angles are. It's in a different shape. But when you're looking at the similarity, you have to be very careful about which sides are equivalent to which other sides, which sides are in proportional to which other sides. So in this example over here, for example, we have to figure out what A is, what side A is, and what side B is. If we just look at it with the naked eye, it looks like A and B are corresponding to each other, but they're not really corresponding to each other. The one opposite the 100 degrees corresponds to the one opposite the 100 degrees over here. Here's where we can figure out the ratio between the two triangles. So the 18 is proportional to the 12. So now let's compare the one opposite the 30. So the ratio, by the way, as you can see, is a 3 to 2 ratio. 18 to 12 is the same as 3 to 2. So we can write up here, for example, that this has 3 for every 2 that this has. So we can figure out the other angles relatively easily. Opposite the 30 is the 4. So the 4 is going to be proportional to the one opposite the 30 here, which is the A. So if there are 2 here for every 3 here, we know that if this is 4, then the A has to equal 6. Because 2 to 3 ratio, of course, 4 is multiplied by 2, so 3 multiplied by 2 is 6. Now let's figure out what B is over here, and we'll use a different color to symbolize that it's a different proportion. B is the one opposite the 50 degrees. Well, what's opposite the 50 degrees? The 15 here. Now, the 15 is 5 times 3, so the B will be 5 times 2, and the B will be 10. It may help, by the way, and let me get rid of this and put the original triangles back up over here. It may help to visualize the shape turned so that it's more comparable. For example, if we rotate this, rotate, let's say 90 left. No, okay, that other way. Let's rotate it back. Rotate right 90. Okay, is this? Okay, well, it's the opposite. Is there any way we can flip it over here? Flip horizontal. Yeah, I guess this is kind of comparable to there. Alright, anyway, I'm just trying to flip it to make it look like this one. I'm not doing a very good job. But anyway, you see the point. The point is you have to always make sure that the sides are in proportion relative to the angles that they're opposite. If you can't keep track of it, just try to see, okay, what angle is it opposite, and that's the one it is in proportion to. This is an example of an angle that is proportional. Excuse me, similar, two angles that are similar to each other. And that is a general principle that if you have two triangles that are formed, really, a big triangle and a small triangle, the big one is ABC, that's this whole thing over here, whereas the small triangle, CEF, if these two lines are parallel, if EF and AB are parallel, by definition this means that the two triangles are similar. Let me put this on the big board a little bit over here just so that I can draw on it. That'll just take 1 second over here. Sorry, maybe I shouldn't do this with the recording running, but that's okay. Okay, there we go. Let's bring this over here. Okay, there we go. we have this over here. Now, if these two lines are parallel, if this line is parallel to this line, that means that the two triangles, the smaller triangle ECF and the bigger triangle ABC, are parallel to each other, are similar to each other. The reason is of course, this angle is an angle that is in both triangles. Angle C is in the smaller triangle and the bigger triangle. And if these two are parallel, that means that consecutive angles, this angle over here, let's say angle 1 and angle 2, have to be equal to each other. They're consecutive angles. I mean, there are many. We didn't really prove that yet, but if you want to understand why, there are many reasons why. One reason is because this has to be equal to this based on alternate interiors. Actually, whoops, I'm sorry. If you'd extend this line over here, this has to be equal to this based on alternate interior angles, the general rule of parallels, and then this has to be equal to this based on the rule of vertical angles. So if we call this angle 3, angle 1 has to equal angle 3 because they're alternate interiors, because these two lines are parallel, AC is a transversal, and 2 has to be equal to 3 because they're opposite sides of intersecting lines, they're vertical angles, they have to be equal as well. So anyway, but the point is, so consecutive angles are equal, so this angle 1 has to be equal to angle 2, and if we put a 3 and 4 over here, angle 3 has to be equal to angle 4, and therefore the three angles are all equal to each other. So the sides are all in proportion. For example, let's say we know that CF is 10 and CB is 15. So we know that there's a 2 to 3 ratio between everything that's over here and everything that's over here. So for example, if this CE is 12, so again we have to keep that same ratio. We have to keep this as a 3 to 2 ratio, so this would have to be 18. If this, for example, is 8, EF, so AB has to be again a 3 to 2 ratio. AB would have to be 12. The next section is about trigonometry. Now, the section in the study guide about trigonometry over here is very detailed and very interesting. It goes through the history of trigonometric relationships, and it goes through the reasons for everything, and it proves things, and it explains why things work and all that. I'm not going to go into it in that much detail because, it's great to know the background, and if you can read this and understand it, that's absolutely positively fantastic. But I don't think you necessarily need all of the background. I'm just going to give you the basics, the stuff that you need for the course. And that's a basic understanding of trigonometric relationships. Trigonometry is the study of the relationship of the angles of a right triangle to the sides of the right triangle. It only works for the right triangle. I mean, there are other trigonometric applications in non-right triangles, but for the time being, we're only going to worry about right triangles. A right triangle is a triangle with a right angle, as we know. There are 3 sides to a right triangle, 2 legs, and 1 hypotenuse. Every right triangle has to have a hypotenuse, and the hypotenuse is the longest side of the right triangle. It's the angle that is opposite, the side that is opposite the right angle. Now, the trigonometric relationships are the sine, the cosine, and the tangent. And these are relationships that regard to any particular angle. Let's take this angle over here. We're going to call it by the Greek letter theta, which is usually used for whatever reason in figuring out in using trigonometric functions. The rule for sine is that theta, namely the sine of theta, the sine of an angle, is the opposite side divided by the hypotenuse. I'm just going to write hy for hypotenuse. The cosine of theta is the adjacent side over the hypotenuse, and the tangent of theta is the opposite side over the adjacent side. The way I've was taught in high school to remember this, and the way most people are taught in high school to remember this, is to remember the word SOHCAHTOA. Now, you may not. Obviously, you have to remember how to spell it, because if you don't know if you don't know how to spell it, then it's kind of pointless. But so it means the sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tangent is the opposite over adjacent. This is a particular number that applies to every right triangle, and it applies based on the angle in question. Now, there are charts all over the place online in terms of how to figure out, and just there are literal charts. I mean, there's every angle has a particular set of numbers. 30 degrees, I think, is actually it lists some of the relationships over here. What is it? The sine of 30 degrees happens to be a half. The cosine of 30 degrees happens to be hypotenuse over 2, whatever it is. The sine of 6. Anyway, the point is that there is a specific number for every relationship, and you can either look at it. In the old days, we used to have a chart, like on the regions when I was a kid. When we took the trigonometry regions, we'd have a chart that would tell us the sine, cosine, and the tangent of each particular number, and that's the only way we'd figure it out. Today, you're allowed to have a scientific calculator. Certainly, you should have a scientific calculator, or at least that has trigonometric functions when you're taking the final exam. This is an example of a business calculator, but it does have the trigonometric functions. You can see it has the sine, cosine, and the tangent. Most good calculators will have these. Really, anything but a very basic calculator will have the trigonometric functions, sine, cosine, and tangent. So, for example, if I want to know what the sine of 30 degrees is, I would just input 30 and press sine, which is the blue, so the 30 is 0.5, which is a half. If you notice, by the way, the sine and the cosine have to be under 1. Cannot be 1, because the hypotenuse has to be the longest side of any right triangle. Because the hypotenuse has to be the longest side of every right triangle, and the hypotenuse is the denominator of both the sine and cosine function, it cannot be as much as the hypotenuse, so it has to be under 1. Tangent, on the other hand, could be more than 1, could be infinitely high, it could be infinitely low, or I shouldn't say infinite, but almost, it can get very, very high or very, very low, and so you need to input. So, for example, if you have an 89-degree angle, let's say, and you want the tangent of an 89-degree angle, you'd click 89, and then click the tangent button, and it's 57.29, which means if it's an 89-degree angle, opposite is 57.29 times as long as the adjacent. So with respect to this particular angle over here, the opposite side is here, so I'm going to put a little O, because this is the opposite side of the hypotenuse. And this, of course, is the adjacent side, and this is the hypotenuse. So the sine of theta, the sine of this angle over here, would be this divided by this side. The adjacent would be this divided by this side, and the tangent would be opposite over adjacent. Now, there are also 3 other functions that go along with it. We've had 3 ratios: this over this, this over this. This over this, this over this, and this over this. If you're wondering, well, are there also functions for this over this, and this over this, and this over this? The answer is yes. Those are called the cotangent, the secant, and the cosecants. But you know what? We don't have to worry about that yet. If you take calculus, you take more advanced math courses, you'll learn all about those functions and their applications. But these are the only ones we really need to worry about for this course, for basic trigonometry: the sine, cosine, and the tangent. So, for example, if I tell you that this is 30 degrees, and I tell you that the hypotenuse, let's get a different color. Okay, let's say I tell you that this is 30 degrees, and I tell you that the hypotenuse is 10, and I want to know the opposite, well, we could figure that out using the sine formula. Remember, the sine of 30 degrees equals the opposite, which is x, we don't know what the opposite is, divided by the hypotenuse, which is 10. What is the sine of 30 degrees? Well, let's do it on the calculator. We just did it, but let's do it again. the sine of 30 degrees, well, put in a 30, put in a sine, and we get 0.5. So then we could solve this as we would any other very simple equation. It's 0.5. So 0.5 equals x over 10, and a simple basic cross multiplication would get you x equals 5. So if this is 10, that has to be 5, assuming this is 30 degrees. Now, we could also figure out what the adjacent is. Now, we can't use the sine formula because the sine formula doesn't take into account the adjacent side. But we could either use, now that we have the opposite and we have the hypotenuse, we could either use the cosine formula, which is a over h, or we could use the tangent formula, which is o over a. You know, let's do both just to make sure that they come out the same. If they don't come out the same, we got a problem. Okay, well, I don't want to snip off that little corner of the triangle. So I'm going to do this again. Okay, there we go. So let's figure out what the adjacent side is in this triangle, assuming a 30-degree angle. Well, let's figure it out using the cosine formula first. What is the cosine formula? Well, what's the cosine of 30 degrees here? And by the way, you might have also realized that if this is 30 and that's 90, this has to be 60. Now, if this is 60, we could actually, if I'm looking at this angle here, well, then this becomes the opposite, and this becomes the adjacent, because that's the one next to the angle. The hypotenuse, of course, stays the same. So if we wanted to, we could say this is 60, and then we could use the sine formula. If for whatever reason we just wanted to keep using the sine formula for whatever reason, we could use the opposite over hypotenuse to get that. But you know what? Let's use the cosine formula for 30. Now, what's the cosine of 30? Well, I don't know. So let's bring up our calculator. Let's clear it. And the cosine of 30 is 0.87. It's probably not an exact number, but we'll round it off. The cosine equals the adjacent over the hypotenuse. So the cosine of 30 is 0.87 equals the adjacent, which we don't know, we're going to call it x, over 10. Okay, well, simple cross multiplication, x times 1, and you can put that over 1. 0.87 times 10 is 8.7. So the adjacent is 8.7. Just for kicks, let's also do it using the tangent formula. The tangent formula, let's delete this and see if we get the same answer. Tangent formula is opposite over adjacent. Well, let's figure out the tangent of 30 degrees. Okay. 30 tangent is 0.58. Okay. So the tangent of theta, which is 0.58, equals the opposite over adjacent. Opposite is 5 over the adjacent, which we don't know what it is, so we'll call it a. Let's call it x, because we don't know what it is. And then let's use simple cross multiplication. 5 times 1 is 5, equals 0.58x. Divide each side by 0.58 in order to isolate x. You've got 5 divided by 0.58. Again, we probably should be able to do this in our head or on paper, but let's do it on a calculator anyway. So we've got 5 divided by 0.58, and lo and behold, 8.62. So before we got 8.7, but it's probably because they were both rounded a little bit, and if you did the full number, everything's been rounding off to 2 places, it would be the same result. So we got 8.62, which again rounded. In this case, it would I already said that it's the same result as we got there. So that is basic trigonometric functions, and the idea here, like in the book, it gives you. I'm sorry, in the study guide, it gives you an area formula where you can use this to figure out the area. I would recommend just using it, keeping it in the back of our minds that we know the area formula for a triangle. It's base times height divided by 2. For a quadrilateral, it's simply base times height. We discussed that. Sometimes, if you don't know what a particular side is, you may be able to figure it out using trigonometric functions. let's kind of keep that as a tool in our arsenal that we'll need to figure certain of these things out. Lesson 6 in the study guide over here involves circles with angles. Now, this is a little bit of a more complicated section of geometry, but we do need to do circle geometry. Certainly, the rules are, the rules aren't that complicated, but just they're a little bit newer, a little bit less intuitive. And that's because of this idea that a circle is not as neat as a quadrilateral. A quadrilateral, the area, base times height. For the perimeter to how long it is to go all the way around a quadrilateral, simply add up all the sides. Well, with a circle, it's a little bit more complex because a circle has this new concept of pi. We talked about pi a little bit earlier. Pi being a constant number, a number that's always the same. Throughout the history of the world, pi is always applied to a circle equally. And it's approximately a number that's about 3.14, about 22/7. Again, 3.14159 is actually the first 6 digits of pi. But pi is an irrational number. It does go on forever. And pi is defined as the ratio of a circle between its circumference and its diameter. So in this diagram over here, this diameter, if this is 1, the diameter, then the circumference is pi, which is about 3.14159. Very important ratio, as you can imagine, whenever anything is being designed. If you're designing a circle and you want to know how much material you need to cover the outer edges of the circle, to cover a fence in the circle, well, it's not so easy to actually measure the outer edges of a circle. It's not flat. Tape measures don't do so well when you're talking about circles. So it's much easier to just measure the diameter, which is a straight line. Once you measure the diameter, all you need to do to figure out the exact amount of the circumference is to multiply it by pi. Also applies when you're talking about the area of a circle. Area of a circle, as you may recall, is pi r squared. A few other things, a few other terms in a circle. There's the radius, which is simply the line from the middle, the line segment from the middle to the edge. Diameter is all the way across. A line segment that doesn't pass through the middle of a circle, but goes from point to point, is called a chord. And the measure of the perimeter of a circle, or the circumference of a circle, part of a circumference of a circle, is called an arc. An arc is this darker line that goes from here to here. Now, of course, radii, diameters, and chords are measured in distance. Arcs, on the other hand, can also be measured in degrees. And that's by how much of the entire circle does it take up. As you recall, an entire arc, an entire circumference, if you measure it in degrees, is 360. 360 degrees worth of angles going all the way around a circle. So if you measure it by what percentage of the circle it takes up, you can also measure an arc in number of degrees. For example, if an arc is, let's say, 90 degrees, that means it takes up a quarter of the circle. I don't know how much this particular arc is. It looks like maybe about 70 degrees or so. It takes up about a little less than a quarter of the circle, maybe about a fifth of the circle, give or take. Maybe even a little bit less than that. But that's essentially what the idea of an arc is. Sometimes the term radian is used to measure the the length of an arc, based on the idea that the entire circle, the entire amount going all the way around, is 2 pi radians. Now, as you can probably figure it out, the word radian comes from the word radius. And just like a circumference is 2 times pi times the radius, in other words, 2 pi radii, so you can also make a determination. You can also, instead of calling them angles and instead of calling them degrees, you can call them radians, which is how many radii does the arc take up. In other words, what's the relationship between this radius and the length of this arc? If it's the entire circumference of the circle, then the ratio is 2 pi. The entire arc of the entire circle, the entire 360 degrees, would be 2 pi times the radius. If it's less than that, if it's a smaller number of degrees, it would be less than 2 pi. Half an arc that starts over here and goes all the way around to here, let's say, would be 1 pi. Because that would be half of an entire circumference. I'm not going to worry so much about calling them radians, because to me, for all the purposes of this course, we're perfectly happy calling them degrees. what percentage of the circle does it take up, and divide that by 360. Or what number of 360 degrees does it take up? Let's take a look at the board over here, and let's make a circle. Again, this is not a perfect circle, but it will have to do based on my limited degree of artistry or spatial abilities. Anyway, so we got this point in the middle, and let's assume that's the circle. It's not the circle, but let's assume for argument's sake that it is the circle. Now let us draw imagine that this is a straight vertical line, and this is a straight horizontal line. Okay. Okay. Now, first of all, these two lines, let's assume that they're perpendicular to each other. In other words, they form a right angle with each other. This is a right angle. Now, what's a right angle? Well, all right angles have to be 90 degrees. What is the number of degrees of this arc? This arc, let's say arc AB. The way we would write this, by the way, is AB with a little arc on top. So you call this arc AB. We're not talking about line segment AB. If we wrote AB with a line segment, well, then we would be asking what is the distance from A to B. Distance from one to another is always the straight line. But that's not what we're asking. We're asking the arc. We're asking for the measure of degrees that corresponds to this amount. Now, just from looking at it, it should be, hopefully, common sense that this arc has to be 90 degrees, for many reasons. The primary reason of which, it's 1/4 of the circle. Assuming this was drawn properly, this would, of course, be 1/4 of a circle. If you do put a line here and a line here, you'd have 3 more of the same amounts. So this arc would be 90 degrees. And this shows us the first rule of arcs, and that is a central angle. Now, a central angle is an angle that is formed at the center of the circle is equal to the arc it intercepts. Should be obvious in this case, but it's true regarding any case. So if I have another line, for example, one that goes like this, if this angle is, let's say, 30 degrees, well then this arc AC, let's call it, would also be 30. Okay. The other type of angle is what's called an inscribed angle. An inscribed angle is an angle that is on the edge of the circle, that hits the angle itself is on an edge of the circle. Let's draw it with a different color. Let's draw the inscribed angle something like this. You know, actually, I have a better idea. Let's draw the inscribed angle that goes between A and B. Now, the reason why it's called an inscribed angle is because it's entirely inscribed within the circle. The question is, how do you measure this angle? How much is this angle? Now, if you look at it and you think about it, hopefully it should become obvious that this angle is going to be 1/2 of this angle. Why? Because it's narrower, clearly is narrower, gets to the same point, and it does it in twice the length. Remember, this is the center of the circle. So if this is the center and this is all the way on the edge, well, it has twice the length to get to the same 2 points. So that's going to be 1/2 of the 90, and therefore this is going to be 45 degrees. An inscribed angle is equal to 1/2 of the arc it intercepts. That's the second rule regarding arcs and angles within the circle. And as you can see from this diagram, interestingly enough, you could have many different angles within a circle, many different inscribed angles. And if you look at all three of these are inscribed angles because they all form at the edge of the circle. As long as they all intercept the same arc, and if you notice they all do, this one ends over here and over here, this one ends over here and over here, this one ends over here and over here, they're all the same angle. They're all the same angle, which is equal to 1/2 of whatever the measure of this arc is. Second thing, which again should hopefully be fairly obvious, called Thales' theorem, and that is if an inscribed angle measures a semicircle, inscribed by a semicircle, it has to be a right angle. Let me make this a little bigger to make it a little bit more obvious as to why that is. Okay. Okay, here is our inscribed angle. And let's draw a line going all the way across the circle. And let's assume that this is a semicircle. This whole thing going all the way around is a semicircle. Whoops, like this, going all the way around is a semicircle. And which, of course, means that this also has to be a semicircle. How many degrees of arc is this semicircle? Well, of course, it has to be 180, because it's exactly half a circle, and we know a full circle is 360. So this arc has to be 180, and obviously the other arc would also have to be 180, because 180 plus 180 is 360. Based on that, assuming that this is a semicircle, what must this angle be? Well, this angle has to be 90. Why? Because an arc is always 1/2, the angle of an inscribed angle is always 1/2 the arc it intercepts. So it has to be a right angle because it has to be 1/2 of the 180, which is 90. Now we're going to move on to some rules regarding a circle and some of the rules regarding chords and things like that. Now, these rules can be a little complex, but they're all logical. That's the good news. And so I'm hoping that, there's going to be a little bit of memorization in here involved. You're probably not going to be able to remember all these things offhand, just by very easily. But the thing is, as long as you understand the logic behind them, these shouldn't be too difficult to reproduce, even if you don't remember the rules by rote. First is angles between chords. Now over here is an example of a circle. Within it you've got two chords. None of these are radii or diameters because it doesn't hit the middle. None of these lines hit the middle. If one of these lines hit the middle, then they would be diameters. Then BA, if it went through the middle, would be a diameter. CD, if it went through the middle, would be a diameter. E is not the middle. The middle would be somewhere around here. And by the way, you can never assume that any point is the middle unless it tells you. The conventional way is to call O. As for a center of a circle, you can call it O. And if you call it O, that usually indicates that it's the center. But other than that, I would never assume that something is a center. Okay, now these are angles between chords. These are two chords that cut each other and make angles over here. Here's theta. The point is point E. And the rule is, let me make this a little bit bigger over here so that I can show you things a little bit more easily. So I'm going to make this nice and big. Okay, there we go. Now, the rule is over here that this angle and this angle together, and now we know that this angle and this angle have to be equal. If we have angle 1 over here and angle 2 over here, or angle 3 over here and angle 4 over here, now in general we know that angle 1 and angle 4 are supplementary because they're on the same line. They have to equal up to 180. 1 and 2 are equal because they're verticals. 4 and 3 are equal because they're verticals. 1 and 2 are equal because they're verticals. 2 and 4 are supplementary. All those rules are fine, but in terms of their relationships to the arc, let's say we've got two arcs over here that are bolded. We've got arc BD, and we've got arc AC. Now, if these were central angles, then of course angle 2 would be equal to arc AC, and angle 1 would be equal to arc BD, but unfortunately they're not central angles, so you cannot establish that. What you can do, however, is that angle 1 plus angle 2, and I'm hoping that this will be pretty obvious once we discussed this rule. Angle 1 plus angle 2 is the same as arc AC plus arc BD. This angle and that angle, the angle 1 doesn't equal arc BD because it's not a central angle, but when you combine them, when you combine the areas swept out by these two angles, regardless of the fact that these are not central angles, they have to equal the entire amount of the arc. Whatever arc is swept out over here, for example, let's say this arc BD is 60 degrees, and arc AC looks like 120 degrees, let's say. Let's just say, for argument's sake, that this is arc 60, this is 60, and this is 120. Well, that means these two combined, these two arcs combined are 180, which means that these two angles, that would also mean that angle 1 plus angle 2 is 120 degrees. So, for example, if I told you that angle 2 equaled 100 degrees, well, then you would know that angle 1 has to equal 80 degrees. Notice, of course, well, actually, that makes no sense whatsoever, and the reason why that makes no sense whatsoever is because these angle 1 and angle 2 have to equal each other. They're vertical angles. They have to equal each other. So, actually, angle 1 plus angle 2 actually have to equal 180, which means that angle 1 is 90 degrees and angle 2 is 90 degrees in this particular case. Because combined they have to equal 180, they have to be equal to each other. So really, the way this is said in terms of mathematical formulas is that the two angles combined, CBA, which is the rule over here is a rule that regards the inscribed angles. But in terms of this rule, the rule is that each angle, angle 1 and 2, have to equal 1/2 of whatever the combined arcs that are swept out. The next rule over here, we've got angle CBA, which is this inscribed angle. Let's go back to here and put the same figure up. Make it nice and big so that we can see it. Okay. So the next rule over here is that angle CBA, which is the inscribed angle here, plus angle BCD, which is this over here, have to equal 1/2 of these two arcs. And that, again, should be obvious as to why. Because this angle sweeps out arc BD. Angle C, or angle 1, let's say, sweeps out this arc, sweeps out arc BD. This angle, angle 2 we'll call it, CBA, sweeps out this arc, because the ends touch over here and over here, so it sweeps out arc AC. And we know in general that an inscribed angle is 1/2 of whatever the arc is. So therefore, this plus that, angle 1 plus angle 2, is 1/2 of these two arcs combined, is 1/2 of arc AC plus arc BD. I hesitate to even write that as a formula because you really shouldn't need a formula to know that. That should be apparent to you. That should be obvious to you. If all inscribed angles are 1/2 of whatever the arcs that they sweep out, well then any two inscribed angles have to equal 1/2 of whatever the total amount that they sweep out is. So for example, if I know what arc BC is and I know what arc AD is, I can figure out what the other two are as well. And finally, let's look at tangents and secants. Now, tangents and secants are kind of like chords and things like that, except the lines don't start in the circle. Chords are lines that start in the circle, and line segments that start in the circle and end in the circle. Tangents, on the other hand, are lines or line segments that start outside the circle and run up right alongside of it. You can see what a tangent does. It doesn't go into the circle, but it hits the edge of the circle. Starts over here, runs along here, and hits the side of the circle. and then the other side of the tangent also hits the edge of the circle. Then there are something different called a secant. A secant is also a chord. It's also kind of like a tangent, except rather than running off the side of the circle, it goes through the circle, hits the circle's circumference twice. For example, this secant hits the circle's circumference over here, and this secant hits the circumference over here and over here. And there are a whole bunch of rules that are relevant to this. And the next lesson is going to cover, what these rules are. For now, I just want to introduce the concept. And so the first rule is the rule regarding the angle. What is this angle over here? What is theta? And the rule is actually very similar to the rule of an inscribed angle. Remember, if the angle was inscribed, then it would be 1/2 of whatever it sweeps out. Well, the rule for this is similar, except that you have to take whatever it sweeps out, and you have to subtract whatever's on this side. You kind of have to imagine this entire thing being shifted to the left. For example, let's draw this. I just put it in. Let's draw a circle that's separate. Let's draw a nice little black circle, and let's do an inscribed angle instead. If we did an inscribed angle, so an inscribed angle would look something like this. And let's, just like in the other diagrams, let's color the arc that it sweeps out blue. Okay. Sorry if it's not drawn very well, as usual. All right. So this, of course, is going to be the measure of the arc is 1/2 of the angle here. So if we call this theta, that means the measure of angle theta is 1/2. If this is arc AB, is 1/2 of arc AB. Okay, that's what we learned before. Now here, the rule is going to be very similar, except that the angle is actually outside the circle. So you have to subtract the amount that, the red arc. You have to subtract the amount that this is taken outside the circle. As if this were drawn further out to outside the circle, it would be a smaller angle. I mean, try to envision these lines. If we drew these same lines over here, but we drew them to a point outside the circle over here, well, you can see this angle would obviously be a much smaller angle. And the way you compensate for the fact that it's a smaller angle is you take the arc AB, but you have to subtract this arc in order to get the total. So that's what you do over here. That's what you do with these top diagrams over here. You take the blue arc, which is the arc that's intercepted, and you subtract the red arc, and then you take 1/2 of that. So for example, if the blue arc in this case is, let's say, 220 degrees, let's not use red because this is red, let's use a different color. Let's say this is 220. So that means, of course, this has to be 140 because they have to equal 360 altogether. So if you take 220 minus 140, you get 80. And then it's 1/2 of that, like an inscribed angle. So this angle would be 40 degrees. Theta would be 40 degrees. Same thing as when you have either one tangent and one secant, as in this case, or two secants, as in this case. If we have, for example, the arc over here being 100 degrees, and let's say this arc over here is 30 degrees. Well, okay, what's the difference between the arcs? 100 minus 30 is 70. Divide that by 2, and your measure angle of theta is 30 degrees. Over here, let's say this looks to be about, let's say, 200 degrees. Now this doesn't have to be the full, this doesn't include the entire circle, so this arc is not going to be the full 160. So let's say this arc is 100. Well, then the difference between the arcs, 200 minus 100 is 100, divided by 2, and theta in this case is 50 degrees. One last rule for this lesson, that is cyclic quadrilaterals. The idea is if you circumscribe any kind of a quadrilateral, it doesn't have to be a parallelogram, doesn't have to be a rhombus, square, trapezoid, doesn't have to be any of those things. In fact, I don't know if you can do a trapezoid in a circle. In a circle, yeah, I don't know if that's actually maybe it is. Just thinking whether, yeah, I guess it might be. I don't know. Anyway, the point is, if you take any kind of a quadrilateral and circumscribe it in a circle, the only way to do that is to draw it so that opposite angles have to equal up to 180. Opposite angles have to be supplementary. So for example, this angle, angle D, and angle B would have to equal up to 180. The logic behind that is actually fairly simple, because the opposite, if you have a quadrilateral like this in a circle, let's draw a separate quadrilateral on the whiteboard so that we can mark it up a little bit. So this is another example, just a random example where I put a random quadrilateral into a circle. So let's name the points. We'll name this A, this B, this C, and this D. We'll just call the angles 1, 2, 3, and 4. Now, if angle A, of course, is half of this arc that it intercepts, half of arc angle 1, we'll say, is 1/2 of arc DCB, or BCD. It has to be, obviously, because this arc sweeps out from here all the way around to here. And angle 3, which is its opposite, has to equal 1/2 of this arc that goes angle C, right? Ends here and ends here. So it would have to be angle BAD, 1/2 of angle BAD. Now, if you notice, that's the entire circle. If you combine the arc that C sweeps out and A sweeps out, since they meet at the same point, it has to be the entire circle. Now, if it sweeps out 360 degrees, half of 360 is going to have to be 180. So angle 1 plus angle 3 has to equal 180, and by the same token, angle 2 plus angle 4 has to equal 180. And, of course, that also makes sense because all 4 angles in a quadrilateral have to add up to 360 altogether. The next lesson is relevant to finding out the distances, the physical distances, the lengths of arcs and line segments that are relevant to all the things that we've already been discussing. Now, the study guide over here gives you specific formulas to figure out arc lengths with regard to the degrees. I don't even think you need that kind of a formula. What I would do is I would just use it based on a logical perspective of what we've already covered. Let's say we have a circle, a fairly simple circle like this. Let's say assume that O is the center of the circle, and of course this angle over here, BAC, is an inscribed angle, BOC is a central angle. How would you describe the relationship between these lines and the arc of BC? Well, of course, OB and OC are both radii of the circle. They have to be the same length because every radius in the circle is the same length. AB and AC, of course, are chords, which don't necessarily have to be the same length. In this case, they look to be fairly similar in terms of length, but that's just a coincidence. They don't necessarily have to be the same length. What if I'm giving you OB? What if I'm giving you, let's say, the OB is 5, and I tell you that this angle is a 60-degree angle. Is there any way to figure out how long BC is? Well, without having to memorize everything, I would say right away, of course, the answer is yes. The way I would do this is very simple. First, figure out the entire circumference of the circle. Then, simply figure out what percentage of the entire circle BC is, and divide. What is the circumference of a circle? 2 pi r. 2 pi times the radius. The radius is 5. 2 times 5 is 10. So the circumference is 10 pi. If we want to round that off, we could round off pi to 3.14. So multiplied by 10 would be about 31.4. Okay, now, arc BC is what percentage of the circle? Let's figure it out. The entire circle is how many degrees? 360. This particular arc is based on a central angle, which means it takes up what percentage of the circle? 60 degrees. Remember, an arc is equal to the central angle, so this arc is 60 degrees. 60 over 360 is 1/6. So to figure out what percentage of the entire circumference is, simply divide by 6. And I'm going to take 31.4, and I'm going to divide by 6, and I get 5.23 approximately. So the length of the arc, circumference of arc BC, would be approximately 5.23. If you were given this, let's take out all the assumptions and start the problem over. Okay, let's change our assumptions a little bit. And let's say we get rid of the thing in the middle. The only thing we have is AC, which is an inscribed angle. And let's say you were told that the radius of this circle, we don't have any drawn, but that doesn't mean there aren't any. The radius of this circle is 10, and you were told that BAC, angle BAC equals, let's say, 40 degrees. Well, can you figure out what the circumference of the arc is? Sure you can. Well, the first thing you got to figure out is, okay, what is the angle that this takes up? Now we know that this angle is 1/2, since it's an inscribed angle, it's 1/2 of the measure of the arc it sweeps out. So if this is 40 degrees, then the arc it sweeps out has to be 80. So I'm going to put 80 degrees over here as the arc. Let's take the circumference of the whole circle, 2 pi r. Radius is 10 in this case. 2 times 10 is 20. So the circumference of the entire circle is 20 pi. We'll round off 20 pi to 20 times 3.14, which is 6.28. Sorry, 62.8. So the entire circumference of the circle is about 62.8. What percentage of the entire circle does it take up? Well, it takes up 80 out of 360. Now 80 into 360, in terms of a percentage, I'm just doing it on my calculator here, is 22.2%. Really it's 0.22 bar. And so therefore, in order to convert this, I just have to multiply it by 22%, or multiply it by 0.22 bar. So I'm going to multiply that by 62.8, and I'm going to get approximately 13.96, rounded off. So the circumference of this, as it's swept out, is approximately 13.96. A couple of other rules regarding the lengths of chords, the lengths of the segments over here. And that is, the first one is that the products of the two segments that are broken up by chords are equal to each other. The multiplication is equal to each other. Let me show you what that means. I'm going to get this figure over here and put it up on the board. And we'll put this up. There's another diagram there, but I'm going to put this one because I think it's a little bit easier to illustrate. Let's make some points over here. Let's make point A over here, point B over here, point C over here, and point D over here, and point E in the middle. E will be this where they intersect. Now the rule is the product of these two segments that are broken up by the arc equals the product of these two segments. So essentially, ED times EB is equal to CE times EA. Let me move this over a little bit so you can actually see the whole thing. Okay. Because the segments of each line, this is true for all chords. As long as you have two chords that are in the same circle, the length, and you measure the distance from the end of the circle, this kind of proportion works. So in this example, basically it'll mean, if we're trying to figure out what x is, we're trying to figure out what AC is. We know that AE is 6, DE is 8, EB is 3. So the way we'd figure out would this be is this times this, or 8 times 3, is the same as this times this, or 6 times x, and figuring out this is just a very simple equation. 24 equals 6x, and divide each side by 6 to isolate x, and you have x equals 4. And okay, two more rules. Let's look at two more rules, and I'm going to draw, these are unfortunately, again, the sort of thing you're just going to have to remember. So let's draw a tangent, two tangents. The first one is actually a fairly obvious rule. Let me get it a different color so that we make sure. If you take a tangent, a point outside the circle, and you draw two tangents to the circle, there can only be two tangents from any one point, one to one side and one to the other. Maybe you figure that out. These two tangents have to be the same length. Whatever the length of, let's call this A and this B and this C over here, assuming that they're tangents, assuming that they come along the side of the circle over here, they hit the side of the circle. There can only be two tangents, one on each side, and segment AB has to equal segment BC. That's a fairly simple one. It's a fairly obvious one, and if you try it, you'll see the same. It becomes almost obvious. If you have if you have a point over here and you have to draw a point to the circle, one of them is going to have to go this way, and the other is going to have to go that way, and you can see how they're going to have to be the same. They're going to have to be the same length. Okay. The other one is a little bit less obvious, but we can draw it anyway because it's just as important to realize. That is, what if you have a secant and a tangent in a circle? I've got a secant here, and I've got a tangent here. Let's give them letters. We'll call this A, and this B, and this C, and this D. ABC is, of course, a secant. AD is a tangent. And the rule is that AD is the mean proportional between AB and the whole thing, and AC. Which means that if you put together two fractions, if you just put AB on one side over here, and you put it over AD, is the same as AD is to the whole thing, AC. In the study guide, it writes the formula a little differently. It writes the formula that AD squared, this line segment to the second power, is the same as the small segment, AB, times the big segment, which is AC. But this is the same thing. I mean, if you think about it, when you cross multiply, AD times AD is AD squared, and when you cross multiply here and here, AB is AC. So it's really the exact same thing. So if we say that this, for example, is 10, and BC is 12, and AB is 8, well, okay, then we can say the small segment, 8, is to 10. Well, actually, that would actually be impossible. If we don't know what AV is, we have this and we have this, but we don't know. We know what BC is. Well, that wouldn't be possible either. So let's just say AB is 8, and we don't know what BC is. We're trying to find BC as x. Okay, let's use this formula. AB, which is 8, is to 10, as 10 is to x. Since we don't know what x is, 8 times x is 8x. 10 times 10 is 100. Divide each side by 8, and x equals 12.5. Although 12.5 is the entire length. So instead of, since this is 8, this would only be 4.5 left. Now obviously this is not drawn to scale, but that's how you would apply this formula.